Good evening, dear students. In our last class, we had started to discuss about Poisson distribution, right? So, today we will try to see the various properties of Poisson distribution. Okay, like we all know, the Poisson distribution is given by PR is equal to e to the power minus m to the power r by factorial r, right? Where m is given by np. So now let's try to find out the mean of Poisson distribution, right? Mean. Now by definition we know mean mu is equal to RPR, right? R equal to 0 to infinite. So this is the definition of mu. So now we will try to expand these terms for Poisson distribution. So for r equal to 0, we have e to the power minus m to the power 0 by 0 plus 1 e to the power minus m to the power 1 by factorial 1 plus 2 e to the power minus m to the power 2 by factorial 2 plus 3 e to the power minus m cube by factorial 3, and this goes on, right? So the first term becomes 0, the second term e to the power minus m by m, plus the third term becomes e to the power minus m square by factorial 1 plus e to the power minus m cube by factorial 2 plus e to the power minus m to the power 4 by factorial 3 dot. We can take e to the power minus m common, so e to the power minus m common gives me 1 plus m by factorial 1 plus m square by factorial 2 plus m cube by factorial 3 dot, and we know this is nothing but the expansion of e to the power m, right? So we have e to the power minus m e to the power m is equal to m. So the mean of Poisson distribution is given by mu is equal to m, right? So by knowing the number of trials and the probability of success of each trial, we can compute the mean of Poisson distribution, right? Now let's try to find out the variance of Poisson's distribution. Again, by definition we know the variance is given by r square PR minus mu square, right? So let's first try to compute this term, because we know the value of mu is m, right? So we'll just compute this term first. So summation r square PR gives me 0 e to the power minus m to the power 0 by factorial 0 plus 1 e to the power minus m by factorial 1 plus 2 square is 4 e to the power minus m square factorial 2 plus 9 e to the power minus m cube by factorial 3 plus dot, right? Now, like you can see, again we can take the term e to the power minus m common from all the terms. So we'll take that e to the power minus m. This gives me 1 plus 2, 1 plus this term goes, so 2m plus the 3 goes, so over here you have 3m square by factorial 2 plus, if you consider the next term, it will give me 4m cube by factorial 3, and this goes on, right? Now if you look at these terms, you can very well understand that we can adjust these terms by separating the expansion terms of e to the power m, because we have 1, we have m square by factorial 2, m cube by factorial 3. These terms are nothing but the expansion terms of e to the power m. So what we will do is we will separate the expansion terms from the rest of the terms. Okay, so we want to group the terms. So this 1 we keep it over here, we will keep one m over here and take the other m, say in a different bracket, just that we are redistributing the terms so that the expansion terms of e to the power m comes into the first bracket. Okay, plus, so m square by factorial 2. Over here we are left with 2 more terms, so we get over here, okay, we have m square by factorial 2. So over here we get a m square, right? Then m cube by factorial 3. One term goes over here, so we are left with 3 terms over here, that is plus m cube by factorial 2, right? Plus this goes on, e to the power minus m. So we have the first, in the first bracket we have the expansion terms of e to the power m cube by factorial 3 plus dot dot. From the second bracket we can take m common, right? So if we take the m common, we get 1 plus m square by factorial 2 plus dot dot. So we can see even this bracket becomes e to the power m, right? So overall we can write e to the power minus m e to the power m plus m e to the power m, right? So it becomes m plus m square. So we have already found out this term. Now we will put it in this equation. So sigma square is equal to m plus m square minus a mu square, and we have already derived that mu is equal to m in our previous derivation, so we can directly put m square over here, so we are left out with m. So for Poisson distribution, the variance and mean both are equal to m, right? Okay, so let's try to solve few problems. So that you have a clear concept about it. Say for example, question 1. If 5% of electric bulbs manufactured are defective, use Poisson distribution to find the probability that in a sample of 100 bulbs, 5 will be defective. 5 will be defective. Okay. So if 5% of the electric bulbs manufactured are defective, we are already given the probability of finding a defective bulb. It is 5%. So if let P solution, P is equal to probability of finding a defective bulb is equal to 5% is equal to 0.05, right? So if 5% of the electric bulbs manufactured are defective, use the Poisson distribution to find the probability that in a sample of 100 bulbs, so it is already given that our number of trials is 100, in a sample of 100 bulbs, 5 will be defective. So it is also said to use Poisson distribution. So we know that Poisson distribution is given by e to the power minus m to the power r factorial r, right? Over here our r is 5 because the variate will take 5 value equal to 5, that is 5 defective bulbs. So we have 5 is equal to e to the power minus okay, minus m, you have to find m. Now m is equal to n into p, right? So it is 5. So we have e to the power minus 5, 5 to the power 5 divided by factorial 5. So this is your answer. Okay, let's solve another problem. Question: in a certain plant, there are on an average 4 industrial accidents per month. Okay, per month. Find the probability that in a given year there will be 2 accidents. Okay, so like you can see in this problem, we are given the average number of accidents per month. So this average is nothing but m. Okay, so our m is given as 4. Find the probability that in a given year there will be 2 accidents. That means the random variable will take value 2. You just need to find the probability, right? We are already given m. So why I decided to solve this problem is, you have to understand this m is nothing but the average. Okay, and we have already found the mean is equal to m. So whenever you are given these kind of information, that is basically our m is given. So now you can solve it very easily. Okay, so like all the previous classes, even this the PDF of this class consists of assignments, so please try to solve them. Okay, one more thing that I would like to tell: if you are asked to fit Poisson distribution in to any frequency distribution, say how to do it. Frequency distribution, if the question is to fit Poisson distribution to a frequency distribution, how you are going to solve problems like that? So the format of those kind of problems are x, that is the variable values x1, x2, and you have the corresponding frequencies, right? f1, f2. So when you are asked to fit a Poisson distribution to a frequency distribution, you need to find the value of m. In this case, m is nothing but the mean of the distribution, that is summation fx by summation f. So what you need to do is, you need to make one more column of fx and find the summation of fx and also the summation of f. So when you divide it, you get m summation fx by summation f, and this will be obviously, once you get the m, you can find the distinct probabilities of all the variables, right? So you have a problem like this in an assignment. Okay, so that's all about Poisson distribution. Now we'll move on to okay, we had studied binomial distribution and Poisson distribution, and now we are moving on to continuous distributions, right? Those two were discrete distributions, but now we are going to move on to continuous distribution, specifically normal distribution, right? So by discrete distribution, we have seen that the random variable or the variate, can take distinct discrete values, right? But in case of continuous distribution, the underlying variable is a continuous one, like say for example the temperature or the age or whatever variables like this, which can take any value. So it is a continuous variable, right? So such kind of a distribution is normal distribution. Let's first see the definition of normal distribution. If x is a continuous random variable, following normal probability distribution with mean mu and standard deviation sigma, then the probability distribution function is given by Px is equal to 1 by sigma root over 2 pi e to the power minus half x minus mu by sigma square, where x can take any value between minus infinity to plus infinity. Right. So this is the definition of normal distribution. So any continuous random variable, and if it follows a normal probability distribution such that the mean is mu and standard deviation is 6, the form of the probability distribution function is given by this, right? If you plot this looks like a bell. It's a famous bell-shaped curve. Okay, so this distribution has a shape like this. Now, whenever you're associated with this normal probability distribution, we can define one more variable which is called the standard normal variate. Okay, standard normal variate. The standard normal variate z is defined by x minus Ex by sigma x, which is nothing x minus mu by sigma. So for a normal distribution, we can define a variable called the standard normal variate, which is basically the variable minus the mean divided by sigma, right? And this is a very important quantity. We will come to know this, why it is so important. It is called the standard normal variate. Okay. Now the standard normal variate z, the probability distribution function of the standard normal variate z is given by phi z is equal to 1 by root over 2 pi e to the power minus half z square, where z can take the value between minus infinity to plus infinity. Okay. So I would like to repeat in brief that if we have a continuous variable x following normal probability distribution, the probability distribution function has the form like this, where mu and sigma are the mean and standard deviations respectively. Associated with the continuous random variable for normal distribution, each variable can be associated with a standard normal variate, which is nothing but the normal variable minus mu divided by sigma. This z again follows this distribution, 1 by that, where it is 1 by root over 2 pi e to the power minus half z square, and the form it because the mean of z, that is mean of z, is equal to 0 and the variance of z is equal to 1. So if you put mean equal to 0 and variance equal to 1, you obviously get this distribution. So this is the distribution of standard normal variate, where mean is 0 and variance is 1. Right? We will be using it in details later, and it's a very important quantity when it comes to normal distribution. Okay. So like we have just now said, okay, before entering into normal probability distribution, I would like to tell you about a few general properties of probability distribution function. General properties of probability distribution function, fx say. First is fx has to be greater than or equal to 0 for all values of x. Secondly, minus infinity to integrating fx in the range minus infinity to plus infinity will give you 1. This is nothing but the if we consider the normal distribution, the shape of fx is like this, and this integration is nothing but the area underlying the curve, right? So this area has to be 1 in case of probability distribution functions. And thirdly, when it comes to probability distribution function, fx dx, this gives me the probability that the variable x has a value between a to b. Okay, so if x has to be greater than or equal to 0 for all values of x. Secondly, the area underlying the curve, entire area underlying the curve, has to be equal to 1. And thirdly, if we are integrating the distribution function within a limit, the physical meaning of this is the probability that the variable can take values between a to b, right? So these things are very important for you to know. Okay, now so specifically now let's try to prove that in case of standard, normal, variate, the mean and variance are 0 and 1 respectively. So we will try to prove these. Okay, so our motto is show that the mean and variance of standard, normal, variate is 0 and 1 respectively. Okay, so first let's try to show the mean. So by definition we know for discrete variables the mean is given by RPR, but for continuous variable it changes to RPR dr, right? So we will use this. So the mean for standard, normal, variate becomes minus infinity to plus infinity z, and the probability distribution function of standard, normal, variate, we have just now written it is root over 2 pi e to the power minus z square by 2 dz, right? This you can solve just in one line. It is nothing but root over 2 pi minus e to the power minus z square by 2 minus infinity to plus infinity, right? Obviously when you put the limiting values it becomes 0. So we have already proved that the mean of the standard, normal, variate is equal to 0. Now we want to prove that the variance is equal to 1, right? So in any case, in normal, the variance, like we know, is defined by x minus x bar square fx dx, right? We already know this definition. Now over here this x bar is nothing but the mean. The mean we have already found out to be 0. So our variance becomes minus infinity to infinity z square, and our pz is 1 by root over 2 pi e to the power minus z square by 2 dz, right? So we need to integrate it by parts. So we are dividing into two functions. One is z and the other is z e to the power minus z square by 2 dz, right? These are my two functions which I have divided it into. So 1 by root over 2 pi, first function constant, integration of second function, this gives me minus e to the power minus z square by 2 minus infinity to plus infinity minus d dz of first function, that is 1, integration of second function, minus e to the power minus z square by 2 and a dz, right? So 1 by root over 2 pi, this term again becomes a 0 on putting the limits, right? So 0 minus minus it becomes a plus, minus infinity to plus infinity e to the power minus z square by 2 dz. Now if you look at this term, this is nothing but the 1 by root over 2 pi minus infinity to plus infinity e to the power minus z square by 2 dz. This is nothing but the probability distribution function of standard, normal, variate, right? We have just defined this, and since we know that if we integrate a probability distribution function from minus infinity to plus infinity, it has to be equal to 1, right? It is a property of probability distribution function. So immediately we get it becomes 1. So we have proved the properties of standard, normal, and variate. In the next class we will try to understand normal distribution in much more details. Today I would like to end my class over here. Thank you.